Okay, so now let's talk about the space complexity of merge sort. So we've already calculated for the depth of merge sort here, which is k or log of n. So what is there else to look into? So notice that for merge sort, it's not the only function that we are calling. We are also calling the merge function. But we should notice that the merge call is sort of separate from our recursion tree, such that when we call merge sort n, we first call merge sort n over 2 and n over 2 and let them finish before calling merge n. So what that looks like is the merge sort n over 2 is put on the stack and then n over 4 and then etc. etc. So only merge or will the merge call will only appear for a certain amount of time and then it finishes and then the current function finishes before we call merge again. So basically the merge function does not exist for all the stack levels. So only one merge call exists in the stack. So we only need to look into the worst case auxiliary space complexity of the merge function and add it to the memory space we need for the recursive calls. So what is the memory we need for merge sort at the worst case? So at the worst case, we need to create a temporary list that contains all of the elements of the list when we merge the final two partitions. So this means that it has a linear space complexity since it would have exactly the number of memory units needed for the list. So the memory we need for recursion is just a recursion depth times c. So c log n plus the linear space we need for the merge function, which is n. So all in all, the memory or the auxiliary space complexity of merge sort is O of n or linear. So we get a log linear running time for a linear space complexity. So as a disclaimer, this is only true for the current implementation we have. There might be other implementations which might use more or use less memory than linear time. So specifically speaking, for this implementation of merge sort, it pays a space complexity of n to achieve a time complexity of n log n.